All right, hi again, class. So, pre-lab lecture part 2. This is typically what we would do in GIL if we were doing pre-lab lectures in GIL. So we're going to take this offline. The purpose of this activity is to actually help us understand ideal gases a bit more, and to really kind of understand what how we can actually use the ideal gas law equation. So, key concepts from this GIL lecture. With gases, we're going to see the relationships among pressure, temperature, number of moles, and volumes. We're going to actually give you that mathematical description, which is the ideal gas law, and we just went over that in part 1 of the pre-lab lecture video. We're going to learn about manipulating the equation, and then we'll review moles just in case. All right, so this pre-lab lecture worksheet has a couple models that we're going to be working with. So model 1, here we have a representation of the molecular view of water in a closed container at 20 degrees Celsius. All right, so temperature is not very important at this point. Something I want you to consider. Okay, so consider model 1. What are the main differences between a gas and a liquid at the same temperature? So we have a vial here, they're at the same temperature. What's the main difference? Pause this video, think about it, and then let's resume. Okay, I've assumed that you've paused this video and thought about it, so let's go ahead and take a look at this. Well, the liquids, what I'm seeing here is that they collect at the bottom. And the molecules of liquids, if you looked here, they're actually in contact with one another. So their molecules are in contact with one another. Now, what about gases? This vapor here, so these are the gaseous molecules. Well, gas molecules, they fill the container, so liquid molecules settled at the bottom of the container. Gas molecules are filling the container. And what else? The molecules are actually far apart from each other. From one another. So this is what we've been referring to all along at the beginning of the semester. So again, liquids, they condense at the bottom. The molecules are in touch with one another. They collect at the bottom. The molecules are in touch with one another. With vapor, the molecules are filling the container, right? And they are actually far apart from one another. Okay, let's take this a step higher. We have a second model now, and we have 5 different vials with different measurements under each vial, or excuse me, different conditions under each vial. These doubles here are molecules of nitrogen gas, and these singles here are atoms of just helium. Okay, so critical thinking question number 2. Name and give the 4 variables that are used to describe gases. So if you forgot that, pause and go to the part 1 of the pre-lab lecture video. All right, I'll give you about a minute. All right, I'll assume you've paused. So remember, we've just said it was pressure, volume, temperature, and moles. So pressure, volume, temperature, and moles. All right, let's keep going. Compare containers A and containers B. What is the same and different in each container? Does the type of particle have any effect on other properties? Okay, what's the same? Let's actually go with the next question. What's the same, or does the type of particle have any effect on the properties? Let's see, well, we only know because these are the properties, right? So these are both the same size containers. Temperature is the same, pressure is the same, volume is the same. So no, the type of particle does not have, does not have an effect on the other properties. So temperature, pressure, and volume are the same, regardless of the type of particles. Type of particle. All right? Okay, let's take this a step higher. Compare containers A and C. Okay, we're going to compare these two. How does the pressure of a gas change when the number of molecules in the container is doubled at constant volume? All right, so these are both constant volume. You notice this is the only one that's at lower volume. Constant volume, we see that here. And what happens when our pressure, so here our pressure doubled, so they're the same type of molecules or same type of particles. Our pressure doubled, our volume stayed the same, our temperature stayed the same. But what can you notice here? All right, take a minute, think about it. What's different about A and C? Okay, well, when pressure doubles, or we can even say when P increases, what I'm seeing here is actually the number of molecules or number of particles is increasing. So as P doubles or as P increases, N also, and if you counted this, you'll see that N also doubles. And this is all happening at constant volume, our volume's constant, and constant temperature. All right, let's go to the next. How does the pressure of a gas change when the number of moles in the gas in the container is doubled at constant volume? Okay. So let's see. Number of moles is doubled. Okay. So this is actually asking the inverse of this question, right? So number of moles is doubled. Okay. So if the number of moles is doubled, therefore, let's actually take a step back. How does the pressure of a gas change when the number of moles of a gas in a container is doubled at constant volume? Okay, so if here our number of moles doubles, or if we take a look at our pressure, so as N doubles, and we can actually make this general, as N increases, P, or pressure, also doubles. And we see that here. As N doubles, your P doubles, right? So we can say that as N increases, your P increases as well. All right? Okay. Now let's go on to question 6. All right. Considering model number 2, how does the pressure of a gas change when the temperature is doubled at constant volume? All right, let's take a look here. Where's temperature doubled? Constant volume. Okay, so these are constant volumes. So what do we need to compare here? So why don't we compare, let's just compare A and D. All right, let's take a minute and think about this. What happens to pressure as temperature is doubled when volume is constant? And let's add actually something. Volume and amount of moles are constant. All right, pause your video. Okay, I'm going to assume you paused the video and thought about it. So P doubles, your pressure actually doubles. So if we take a look here, our temperature doubled, so your pressure doubles when T doubles. And in this case here, it occurred at constant volume and also constant moles. All right, let's take it a step further. Let's consider this model. How does the pressure of a gas change when the volume of the container is doubled at constant temperature? So we want our number of moles to be constant as well. So we only want to change one parameter at a time, right? Or 2 parameters at a time. So here, why don't we compare A and E? Okay, so here our volume is halved, or our volume is doubled. Our temperature is constant and the amount of moles is constant. What's happening to pressure? All right, let's pause and think about this. Okay, so as your volume is doubled, P halves, so you cut P in half, by half, when your volume is doubled, and this occurs at constant temperature and constant moles. Okay, great. Let's kind of summarize everything that we have here. So in this exercise here, we have the symbol called is proportional to, so when something is proportional to something else. So here I want you to actually consider your answers to some of these questions and circle the correct expression. So based on your answer to critical thinking question number 5, circle the correct expression. So critical thinking question number 5, we said as N increases, P also increases. So that means, is P proportional to N, or is P inversely proportional to N? Pause the video, think about it. You're right. P is proportional to N. All right, let's take the next. So, this should actually say critical thinking question number 6. So in critical thinking question number 6, we saw that at P doubles when T doubles. Or you can also think P increases as T increases. Okay? So based on this, is P proportional to T or is P inversely proportional to T? Pause the video, think about it. You're absolutely right. P is still proportional to T because as one increases, the other increases as well. All right, based on your answer to critical thinking question, this should actually say 7. Circle the correct expression. So here we found that P decreases when V increases. So if we actually write this relationship, P decreases, or P was halved when V was doubled as V increases. So what's our relationship here? You're absolutely right. P is inversely proportional to the volume. So this is kind of just a quick, fun exercise to really understand the ideal gas law and the relationship between all the parameters in the ideal gas law. So remember, the ideal gas law is PV equals N RT. R is a constant. You want to watch out for units, okay? And we'll go over this in greater detail in lecture.